Hello, Hyson here. I would like to show you this remote controlled outlet that I purchased several years ago. There are two pieces. There's a remote with an on button and an off button that control a relay in this box. And what I would like to do is control it using the Yardstick One. So to do that, I need to decode and analyze the communication protocol that these use so that I can send the right bits with the Yardstick One. And we'll do that with a couple of pieces of software. We're going to use GQRX and an SDR dongle to capture the signal. Then we're going to use something else called InSpectrum to analyze that signal and extract the bits from the data stream. And then we'll use RFCat to send that data back with the Yardstick One. So let's get started.
We're at my computer now, and we need to figure out a few pieces of information before we can actually intercept and hopefully replay these signals. The first thing we need to know is what frequency the remote operates at. And looking at the back of the remote, there is an Fcc ID on the back. And if we just type that into our search bar, we'll get several results, but this first one is probably the one that we want. And so this is Fcc.io, which is kind of a nicer, more user-friendly interface than the official FCC database. And we can see that this remote operates at 315 megahertz. And there's a lot of information here. There's internal and external photos, the user manual, the test report, some setup photos, but none of that is really important. What we need is the frequency. I've opened GQRX and I've tuned to 315 megahertz. We're on amplitude modulation mode. I'm going to click the button, the on button, for the remote once and the off button once. Don't know if that was detectable, but the relay in the outlet clicked on and then clicked off. And what we can see as this trace goes down is that it's not exactly at 315 megahertz. So this signal is really at like 314.96 something. So I'm going to click the button again. And we can actually hear the signal. So what I'm going to do is I'm going to record this signal as a WAV file. I'm then going to capture raw IQ data. And I'm going to click it several times. So I'm going to click the button once, twice, 3 times. Then I'm going to click and hold. I'm going to click the off button once, twice, 3 times, and hold. And we'll see the purpose for that in a minute. Now that I've captured the raw IQ and the WAV file, let's look at the WAV file in Audacity. This is the WAV file in Audacity. We can see that there are 2 groups. This first group is when I was clicking the button on, and the second group is when I was clicking the button off. If we zoom in a bit, we can see that there are actually distinct groups within each button press. And so this is pretty typical. You will have the data message, which is some number of bits long, that just gets repeated with a short delay between them. Now on this first pulse, there is this spike and then a decay. This is artifact from the internal circuitry in the remote. It may look, you could probably think of it as a preamble, but it really isn't. And the reason I say it isn't, preamble isn't required by the radio for the outlet to switch on and off. You can see that there's some number of groups here, and if we scroll to the right to where we click the outlet off, I held the button a little bit longer, and so there are more pulses here. And what that indicates is that basically this is going to send this data stream every what is this? Can I even measure that? This is like 0.04 seconds long. So what is that, 40 milliseconds? The important thing to look at is that each of these pulses more or less looks the same. Minus a little bit of noise, it looks like the same high, low pattern for each of these groups. Except this last one, the button was probably released in the middle of transmitting the last group. So we can ignore that. It is certainly possible to manually decode this. You could zoom in here and measure the width of each of these pulses. It's probably safe to assume that this is a 1, followed by 1, 2, 3 zeros, followed by 1, 2, 3 ones, and a 0. So that would be 8 E. And then this looks the same. This would be E8, and then this might be a little different. Anyway, you could do this. You could print it out and use a ruler or a protractor and measure these out. But that's really time consuming and not really efficient. So we're going to use a piece of software called InSpectrum. All right, this is InSpectrum. This is going to take that IQ sample that we recorded, and it is going to decode all of the information that we need directly. You can see that this is quite a long, from left to right, file, and at the beginning it may look like there's nothing, but as we scroll over, we can see here is some data down here. That's one group. There's 5 pulses, and then we can scroll over. Here's 4. Here's a few more, and then this one is going to be quite long. This is where we held the on button down for a few seconds. And then if we scroll way over, here's again 1, 2, 3, and then hold. All right, so how do we go about decoding this file? The first thing that we need to do is we need to right-click. We want to add the amplitude plot. Now, if you didn't know if this was amplitude shift keying or frequency shift keying, this is how we could figure that out. We'll take this window, we'll slide it down over the data that we have. We'll have that center line roughly on the center line of the data. And we want to decrease this shape because we need to get our data to be roughly over this halfway, this dotted line here. Alright, that's pretty good. That's getting a little difficult to see. So let me try to zoom in. No, that's not really helping. Anyway, that's mostly unnecessary. This is probably good enough, but I'm going to add a threshold plot. And what this is going to do is it's going to take, if the signal here is above the dotted line, it's going to classify that as a 1. If it's below the dotted line, it's going to classify it as a 0. Now, there's not a whole lot of separation between these two, and I wish I could change that, but that isn't really an option. If instead this had been a frequency shift keying plot, we would see constant amplitude no matter how close we zoomed in. So in that case, we would add a frequency plot. I don't have any radios that are available to me that are using frequency shift keying. This is great, but we're not really any closer to decoding the signal yet. What we need to do is enable the cursors. Now again, on this first pulse, this is that capacitor spike that we talked about before. So I'm going to zoom in just a little bit, and I'm going to decrease the size of the FFT so that we can see this a little better. And I have this cursor here. And I'm just going to drag it so that the first line meets up over here. And I'm going to take the second part of the window and squish it down so that it makes this downward, this falling edge. Now we need to figure out how many symbols are in this quote-unquote packet. So generally we can try multiples of 2. And if we count the number here, see, we don't actually know. This could be 2 1s, or this could be 1 1. We don't know what width A1 actually is. It's pretty safe to assume that the shortest peak is really just 1 data bit. So let's try 32 and see if we can make 32 match the amount of data that we have. Now this looks pretty good, and we have good alignment on these individual bits, but there's still more signal left. If we tried to stretch this out, it wouldn't work. So where were we? There we were. So since there's about half of the signal left, let's bump it up to 64. Now this looks pretty good. And you may be thinking, well, wait, there are these 3 bits back here that don't have any pulses. That's correct. These are actually zeros back here. So now that we have this lined up pretty good with everything else, what we can do is we can actually extract these symbols and we can copy them to our clipboard And then we can paste this in to a text editor or something else, and we have this series of ones and zeros. And that's not particularly useful. Ones and zeros are kind of hard to compare, and this is only going to plot them for this one data bit that we see. What we would really like to do is we'd like to convert this to hex, because that's going to make it a lot easier to compare. Alright, so we have those symbols copied to our clipboard, and we want to decode them somehow. The easiest way that I know to do this is to use a quick Python script, or the Python console. I'm going to make a variable called symbols with an opening bracket. I'm just going to Control-Shift-V these in. Oh, helps to put an equal sign in. And then to convert those, the best way that I know is to convert these to string representations. And then I'm going to join them together, and then convert them back to binary, and then to hex. And what that shows us is 8E, E8, exactly what we found earlier when we were looking at it in Audacity. And we can again decode this manually off the screen here. So 1, 0, 0, 0, 1, 1, 1, 0, that's 8. And we see 1, 1, 1, 0, that's that's 8. Alright, so I've scrolled over to one of the off pulses. I'm just going to slide this window over again. Because I've zoomed out on this, I've really messed it all up. So we'll slide our symbol window over. See that it's not lined up, so we're going to trim it back. There's still some that are off, so we'll go to the next position. And now here we have all of these lined up. We can extract symbols, copy to clipboard. We can paste it in our Python console. And we can print this out again after we've converted to hex. And, you know, the first time I looked at this, I was like, this is sending the same data both times. But it actually isn't. Somewhere here in the middle, there is an 8E that has been transposed to E8. Or, excuse me, there's E8 that has been transposed to 8E. Right. So we have the symbols that we've extracted as hex. We have the frequency, we have the modulation type. The only thing that we don't have is the symbol rate. And this is also called the baud rate. We can see down here in Inspect From, when we have our data highlighted in the cursor, it tells us what this is. This is 1.68382 kilobaud, which is 1600 baud. Now we have absolutely everything that we need to know. So we can open RFCat. You need sudo to be able to claim the USB interface. There may be a workaround that I don't know about. And this is essentially a Python, an interactive Python console. So we have D, which is our dongle. We need to set the frequency to 314.970.000, which is 314.97 megahertz. We need to set the modem modulation, and that's d.set MDM modulation to mod ASK. Okay. Oops, it's set MDM modulation. We need to turn off sync mode. And then we need to set the baud rate, which is d.set MDM. We can actually use tab completion here. What we're looking for is set MDM D rate. I'm just going to call this 1600. These radios in these devices, the outlet receiver and the transmitter, are really not precise. The frequency doesn't have to be exact. I think you can be, depending on how close you are, you can be up to, 500 kilohertz away from the true frequency and it will still work. And the modem rate is, again, pretty flexible. And what we're going to do now is we're just going to define a function called on. And we're going to do d.rfxmit b I'm going to just paste in this. Now I've encoded this as hex, and that's what this \x 8e is going to do. I've also appended these two null bits to the end. That's going to give us some separation between the end of this group and the beginning of the next group. And we're going to send it 5 times. And then we're pretty much going to do the same thing for the off function. I'm just going to paste this in. Again, note that the only difference between these two is that in the on, this is E8, and in off, it's 8E. And now, if I just send on, that may have been audible. The relay has clicked on, and if I send off, it's gonna turn everything off. So let me do that again, but this time I will take a recording of the device. All right, so I've switched to the phone so that I can record what I'm doing. I'm just going to hit the up arrow twice, and I'm going to send call the on function again, and as soon as I hit enter, the LED turns on, and if we send off, the LED is going to turn off. So let's say we wanted to make this a standalone script rather than having to open RFCat every time. So I've opened Vim, and we're just going to import rflib. And then we're going to d equals rfcat. And then we're going to essentially do the same thing we did over there. In the interactive console, we're going to set three one four nine seven zero 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 d dot set mdm modulation. Set the sync mode, and then we're going to and I've just pasted the same thing in there twice. I'll just call on. I think. Uh-oh. Oops, a couple of errors here. Had to change the import, and I need to capitalize that. And there we go. That probably isn't the best. Yeah, okay. Well, that's it. We've intercepted, decoded, and replayed the information sent by the remote to be able to turn the outlet on and off without it. There are a lot of different things that you could do with this. You could use this as part of a home automation system, or you could be sort of malicious and turn other people's outlets on and off. I do know that these are labeled with channel F. I don't know what the different channels might mean. I don't know if that means different frequencies or different data strings. No idea. Should probably look and see if I can even get another one of these. I bought this so long ago that I don't know if these are still sold. It's unbranded. There's no. I'm pretty sure that I got this at Walmart. There's not really any any information about manufacturer other than what was listed in the FCC report. So, thanks. Hope you all enjoyed. If you would like to see more, please let me know.